So given that we have our equation, we've now been able to express the information in the form of y equals a plus bx equals 194.33 plus 2.396x. We're now able quite easily to do a whole host of other things. Firstly, let's just look at the forecasting idea. Remember, based on the one that we saw before? Forecasting. We want to look at forecasting 850 units level of activity. It's not going to be difficult at all now that we've got our equation. Couldn't we simply say y equals 194.33 plus 2.396x? If we do that, we take the 194.33, the fixed cost remains the same, plus 2.396 multiplied by the forecast units, 850. Slap those numbers into your calculator and you get 2230.9. Now, if you look at this compared to the number that we calculated before, you're going to see that it's subtly different. When we looked at high-low, we came up with a very simplistic answer. That was because we only used 2 pairs of data, whereas now we've used 6 pairs of data. Based on that, we would say that this was a better prediction of what we expect to occur. So, forecasting shouldn't be too difficult. Now, any of the elements that we've looked at so far you could get as a multiple choice question. Either the calculation of B, or the calculation of A, or both, or the use of the formula that we've calculated or been given, this one, to forecast. And I don't think that you'll have any difficulty doing that. But what else can the examiner throw at us? Well, one thing that the examiner may throw at us is something called correlation. Now, when we look at correlation, we are simply looking at how well the underlying data supports the line of best fit that we have prepared. You see, if the data supports the line of best fit very well, we are confident that the line that we have established reflects the data. If, however, it doesn't, then we have to question how good our line of best fit is. So let's just think about it in terms of sketching a few ideas. Now let's start with the extreme values. The correlation coefficient, as we will learn to call it, is given the value R. And we will find that R has a value greater than or equal to -1 and less than or equal to +1. Now, that being the case, let's establish what -1 and +1 means in relation to this. Here are 2 lines of best fit. If we have a situation where all of the data falls on the line, we would describe that as perfect positive correlation. That would have a value R equal to +1. If, however, there is an inverse relationship between x and y, in simple terms, as x rises, y falls. This is an inverse relationship, and we would describe it as negative correlation. If you look at my example, all of the values lie on the line. So here we have perfect negative correlation. Now, In either form, we would be absolutely happy that the underlying data supports the line because of the perfect relationship between the pairs of data and the line itself. The fact that it's positive or inverse, yes, a direct relationship or an inverse relationship doesn't matter. All we're concentrating on is the fact that the data supports the line well. Of course, we certainly may not get perfect positive or negative correlation. So let's just look at a couple of other illustrations. Let's have our positive relationship. Let's just suggest that the data is close to the line, but not exactly on it. Here we may have a value something like r equals plus 0.95. Now we would maybe describe that as near perfect correlation. And if it's near perfect, we'd still be happy that the data supports the line well. And if we extend this just a little bit further, there's our line of best fit as an inverse relationship. And let's just suggest that the data is a little bit further from the line. Remember, these are sketches and no more. Maybe here we would have a value of r equals minus 0.8. Minus to reflect that it's inverse, 0.8 to reflect that, well, okay then, it's certainly not perfect, it's not near perfect, but there is some degree of correlation between the two. If we had data scattered throughout the graph, we would have a correlation that was far, far lower. And the nearer the correlation comes to the value of 0, the less we can say that there is a relationship between x and y. So when we look at the correlation coefficient, all we're focusing on here is how well the data supports the line. Now, in order to do this, what we need is a formula. Again, the correlation coefficient formula is given to you in the tables that the examiner throws at you. Now, if you look at the formula, it's a bit of a monster. And what you find here is the piece of information that we talked about earlier as to preparing but never using is now used. The need for y squared. This formula requires some working. You're going to have to be very careful, so I would strongly advise you to practice this a couple of times to make sure that you can get the numbers out in the exam. Using the numbers that we've already calculated, r equals, well, if you look at the numerator, it's the same as the numerator as we had for the b factor. N was 6. Multiplied by the sum of xy. The sum of xy being 7570000 minus the sum of x, 4000, multiplied by the sum of y, 10,750. We've got that value. You may, just may, want to calculate that separately and calculate the total amount for it, because then we need the denominator. And what we want is the square root of all the values below the line. So what we're going to do is take n, 6, multiplied by the sum of x squared, 2,835,000, minus the sum of x, 4,000, all squared. And we multiply that by n multiplied by the sum of y squared. Remember, this was the value we didn't use earlier. The sum of y squared, 20,252,500, multiplied by the sum of y, 10,750, all squared. Now you've got to make sure that you can get these values out. So I would strongly advise that you sit there with your calculator, bang the numbers in a number of times, and make sure that you're totally happy that you can get this value. If you put all these values in, you will end up eventually with a value of 0.987. And what can we say about that value? Well, yes, first of all, we can say it's positive. There is a positive relationship between x and y. And we've seen that already here because we know that the variable cost rises as the level of activity rises. No problem there. Secondly, I think we could say that it is near perfect. In simple terms, we would be very happy that the data supports the line. I would always expect that the value that we calculate here, this one here, is likely to be 0.9 something. Because if it's less than 0.9, you start questioning the relationship between the pairs of data and the line of best fit that you've set. So we've looked at correlation here, and it really is a case of our ability to be able to bang the numbers in and to get some values out. The other thing that the examiner has a tendency to do is to simply talk about the theory and therefore to highlight the fact that the correlation coefficient lies somewhere between -1 and +1. Right, we're nearly there. We've nearly finished with all this nonsense. The final area that we have to look at with regard to our lines of best fit is determination, or if you wish, the coefficient of determination. Now, the coefficient of determination is where we take the correlation coefficient R and we square it. But what does it mean? Well, the coefficient of determination focuses on this idea. It looks at the dependent variable, in this case, the cost. And the coefficient of determination tries to establish the amount of the change in the dependent variable, y, that is due to, that is determined by, the change in the independent variable. The amount of change in y that is determined by a change in x. So let's just take what we have from the previous example. R squared is going to be 0.987 squared. So if we have 0.987 squared, what do we get? Well, we get something like 0.974. Or maybe to put it in a more sensible frame for us to discuss it, 97.4%. And to use this value, all we would say was this, that 97.4% of changes in cost, that's the y value, are due to changes in volume. You know, the level of activity. And the remaining 2.6% are due to other unexplained factors. Right, so what we've managed to do here is to look at lines of best fit. We've looked at regression analysis, correlation, determination. Oh yes, and at the very beginning, a little bit of high-low. This is very mathematical compared to other aspects of the paper that we're focusing on. But my view is that there are some very easy marks to score in the exam. I would reasonably expect that if you take this whole area, we can get, what, 7 to 9 marks in the exam, and that's quite a lot. And from that perspective, you really must make sure that you are absolutely happy with dealing with this area. Before we leave business maths, now let's look at something called expected values. And if we're looking at expected values, we typically describe them as EVs, just so you're ready for it. If we're looking at expected values, what we're trying to do is to get some sort of value that reflects the overall likelihood of an event occurring and the value associated with it. The reason why we focus on this is because we have a situation where there is probability involved. So an expected value is simply a weighted average value. A weighted average value. Let's look at an example. Let's just say that we have our sales forecast. And the sales forecast could be that we generate £100,000 worth of sales, or £200,000 worth of sales, or £300,000 worth of sales. And then we identify the probability of this occurring. It's possible that 100,000 is our low forecast, and there is only a 0.1 or 10% chance of that occurring. Whereas 200,000 is our most likely forecast, and there is a 0.6 or 60% chance of this occurring, and 300,000 a 0.3 or 30% chance. As we all know, when it comes to probability, probabilities should sum to 1. At least we would hope so. When we're looking at an expected value is simply where we take the sum of P multiplied by X. What I mean by that is that the sales forecast is the value of the outcomes. 100,000 or 200,000 or 300,000. The probability is P. And what we want to do here is to simply multiply the probability by the value. And we would get, what, 10,000 plus 120,000 plus 90,000. Based on that, we find that our expected value is 220,000. So what does this figure mean? Well, as I've said already, the figure is simply a weighted average of the 3 sales forecasts that we have. Being an average value, does that mean that it equates to a value that we forecast? Well, the answer is definitely no. This figure down here doesn't equate to any of the original forecasts. As such, can we achieve the expected value in an individual outcome? Let's say these sales forecasts relate to 1 month. If they relate to 1 month, we cannot achieve the expected value. Either the value will be 100, 200 or 300,000. Therefore, the weighted average only makes sense if there is going to be a repetitive decision or a repetitive outcome each and every month. In that circumstance, it makes sense for us to have an expected value, because on average, once we've taken the mixes of 100,000 and 200,000 and 300,000, we would expect the outcome to be 220,000. So, a couple of observations before we leave this point. 1, it does not have to equal any individual outcome. It's just an average. It could equal an outcome, but that would be luck. Secondly, when we look at expected value, it ignores the risk associated with the outcomes. What I'm trying to get at there is that in the example we've just seen, the range between the worst, 100,000, and the best, 300,000, was, say, £200,000. But it's possible the range could be far wider or far less. The range is not reflected in any way by the expected value. We simply have an average. If you wish, we're losing information. The fact that the range is between 100 and 300,000 does not matter for expected value. All that matters is, as we've said before, the average. If we don't consider the range, we're not focusing on the risk. Now, we would expect something to do with expected values somewhere within your exam. Let's just look at a Mickey Mouse example to see the sort of thing that we may get. A company has the choice of 3 alternative investments. If successful, investment A gives a net present value of 100,000, of which there is a 40% chance. However, if not, it will yield a net present value of minus 40,000. Investment B, if successful, 60% chance will yield 50,000. If not, it will cost us 20,000. And C, 80% chance it will yield 40,000. If not, it will deliver a net present value of 10,000 negative. Now, this term NPV, please don't worry about it. It is simply a measure of return. If you don't like it, just think of it as a profit. Therefore, let's look at the investment. We're looking at the investment A and B and C. Investment A, we have 100,000 multiplied by 0.4. Remember, a 40% or 0.4 chance of success. Together with minus 40. Remember, it was a loss, if you wish. Multiplied by 0.6, the other element. Probabilities must sum to 1. And we end up with an expected value of 16,000. 40,000 minus 24,000. B, 50,000 was the upside potential multiplied by 0.6 plus 20,000 multiplied by 0.4 comes to 30 minus 8 comes to 22,000. And if we look at investment C, 40,000 multiplied by 0.8 plus 10,000 multiplied by 0.2 comes to 30,000. So what would we select? Well, presumably, based on expected values, the best option is option C. It's not based on the overall magnitude of the best outcome or the worst outcome. All we're looking at is the weighted average of what we have there. And what you've noticed is we've got negative values here. And of course, negative values we're going to take away. It's as simple as that. So expected values should not present a problem. You see, expected values will be used a lot when you get into your further studies, F5, F9, maybe even P5. But at the moment, all we're trying to do is to establish some very basic ideas. So we've got a little bit of basic maths here. This is what is described as business maths. It's very possible it will make up, between all elements, about 10% of what you see in your paper. And to my mind, it's the sort of thing that a lot of people don't like. But if you practice and make sure that you can use your calculator properly, I don't think it should present a problem for you. One of the great areas of business maths is that the questions tend to be short and sweet. So if you get them right, you're going to get them right quickly. And that's fantastic when we have objective testing where there's lots of multiple choice.